Hello, in this demonstration I will generate a OFDM waveform on the Rohde & Schwarz SMW vector signal generator and analyze it on the Rohde & Schwarz FSW vector signal analyzer using the VSE software. I have in front of me the SMW interface and can select baseband OFDM signal generation, and we have several choices in modulation type. Today we're just going to stick with a non-filtered OFDM waveform, but we have several options as well. We can specify the subcarrier spacing and the number of subcarriers, as well as the filter settings on this tab here. For this default setup here, it's a sample rate of 20 megahertz and occupied bandwidth of 16.5 megahertz. There are 6 guard subcarriers on the left and right, and that's why we see a difference between this 53 and 64 subcarriers. And that's typical for OFDM signals. We're not filtering the signal at all, but if we wanted to filter the signal to try to improve the occupied bandwidth, we could do so by specifying a user-supplied filter. But for now, let's leave that to none. On the Allocation Settings tab, we can choose multiple users with the data streams that they're sending. We can choose the allocations here. So here we have a QPSK pilot that is 2 symbols long, occupying all 53 subcarriers, followed by a 64 QAM data section. This is where the payload goes, for a duration of 6 symbols and occupying all 53 subcarriers. And then finally, 2 symbols of BPSK pilot. Data source for each of these is pseudo-random bit sequence, PN16. If we had particular data set, we could choose that here as well. Data list, all ones, and so on. Graphically, this appears like this. We have 2 symbols of pilot, we have 6 symbols of data, and another 2 symbols for the pilot. And this was QPSK, 64 QAM, and BPSK. We'll enable that in the baseband, and then set the RF frequency here to 2.4 gigahertz. And we can set the power level here to minus 10 dBm and turn RF on. And now we're generating an OFDM waveform. Now, before we analyze the file, let's go ahead and grab the configuration of this OFDM signal. Since the demodulation needs to be aware of this framing structure here. It needs to know the number of subcarriers, needs to know which subcarriers are occupied, where the pilot is, so it can be able to correct for imperfections in the channel. And so all of that is then going to be available to us from a pre-generated XML configuration file. So we'll change this file filter here. We'll go to K144. We have this exported K144 settings, K96.xml. We'll copy paste that to flash drive and transfer that to the computer that is running the Vector Signal Explorer software. Now here's a view of this spectrum on the Rohde & Schwarz FSW. You can see a signal here at 2.4 gig. Let's go ahead and zoom in on that signal and just verify that it occupies about 16.5 megahertz of bandwidth. Okay, you can drop the video bandwidth here. And we can change the measurement to an occupied bandwidth measurement. You can see here that it's occupying about 16.5, 16.6 megahertz of bandwidth. Okay, so our signal should match. And again, we're not filtering this at all, and so that's why we see this roll-off shape here. If we were to filter that, maybe we would have a little bit steeper roll-off. Now we're going to use the Vector Signal Explorer software. In this case, it's running on my PC, but it could run on the FSW as well. So VSE from preset, let's go ahead and have it connect to the instrument. We're going to connect over high slip, which is a faster connection than VXI11. We'll specify the IP address. Resource string is automatically created for us, and we can connect to the instrument. We are connected and calibrated, and we have some other information about that instrument as well. Jumping back to the measurement tab, we can replace the IQ Analyzer tab with an OFDM vector signal analysis tool. And we are going to be receiving data from that FSW 43 gigahertz, and we'll be looking at the RF input of that signal. To configure, we'll go to the signal description, and we'll load that XML configuration file that we transferred from the SMW earlier. And we'll specify the center frequency, 2.4 gigahertz. And that should be it. We should be able to play that measurement. So now we have the constellation. We can see the 64 QAM data. We can see the QPSK in green here. That's the first two symbols, pilot, and then the last two symbols, pilot, is the BPSK here. We're measuring an EVM, in this case, of minus 46 dB or 0.48%. We also have a power spectrum view, and we're occupying, this is plus minus 10 megahertz. So this is going to be plus minus 8 megahertz for about 16 megahertz. And it's just a little bit wider than that. So I think this is right about on at 16.5 megahertz, as we predicted before. We can change the other settings here as well and reduce measurement time here. And we have a few other settings here as well. We'll start out in the overview block, and this is kind of a summary of all of the settings on the Vector Signal Explorer. Again, we have that loaded K96 file here. We could be able to specify cyclic prefix, input front end. We can auto level the spectrum analyzer to improve the dynamic range, optimized for the current level of the signal. And that didn't make any changes since I'd used minus 10 dBm. But let's go ahead and drop this to, say, minus 50 dBm. Going back to the VSE software, we can now see the constellation. There's quite a bit of fuzz around each of the points here, although, at least in the pilot, there probably aren't any symbol errors. But on the data itself, there are probably some symbol errors. So let's go ahead and auto level the spectrum analyzer, just so that it's optimized for the current input power level. And we can see here, we're getting a respectable 0.7% EVM with this signal at minus 50 dBm input. We can trigger the measurement if we wanted to trigger the demodulation and start right at the beginning of that frame. In this case here, we're capturing significantly more data than is necessary since the frame length is much smaller than the 1 millisecond capture time. But that's just to optimize the measurement speed, so you're not demodulating more than is strictly necessary. We can reduce the result range, search for burst. We can synchronize on cyclic prefix. Preamble is a different form for the OFDM. We can estimate the parameters using the pilots. If we also know the data, then we can also estimate on the data here, and we'll detect based on our configuration file. We can be able to track the signal with phase and time, level, and perform channel compensation to give us the best measurement possible. And then finally, we have some information about the display. And there's a few additional displays as well that we can configure. But this is a quick summary here of how to use the OFDM vector signal generation and vector signal analysis on the Rohde & Schwarz FSW and SMW. Thanks for watching.